Hello friends, good evening. Okay, so I think all of us have clearly understood the formation of depletion layer and the PN junction, the depletion layer. I think all those aspects are clear. If you have any questions on that, you can ask. So before I start with the next section, okay, we will start using the diode now. Okay, so far we have understood what is a diode. Now we shall start using a PN junction diode. Okay, okay. So if you have no questions, we will start. The first thing is now forward biasing. Okay. Now as it is, the diode P and N section, as you know, right? And as I told you yesterday, I have discussed, you have got two terminals here. Of course, I don't have to show it like this henceforth. I think it is quite understandable, but still, for some more classes, I will be showing it like this. Okay, so you have a electrode here and electrode here. This is P and this is N, and this becomes what? Cathode. This becomes anode. Okay, I will not be writing this quite often, but just till we become familiar. Now, what is meant by forward biasing? So here you see you are connecting the P to the positive plate of a voltage source. What is this? This symbol, this is a symbol of voltage source. And here in this case I am using constant voltage source. Okay, hello everybody here, are you with me?
Yes, sir.
Now you have to understand this forward biasing itself. Of course, I am showing a voltage source here so that the voltage is appearing across this. You don't have to show it like this. Okay? You don't have to show it like this. You can just show that for a diode, you are going to supply the voltage like this, and you show it like this. That is, you are supplying voltage V across the terminals. Okay? Now why I am showing like this is because see, what it needs is a potential difference between these two. It needs a potential difference between these two, and this should be more positive than this. What did I say? Hello? What did I say?
That is the potential difference between those two points, sir, and that A point will be more positive than C point.
Here is more positive than this point C. Okay, that is very important. Right. So what I mean is
more positive like not necessarily negative.
Now who can elaborate my word? It should be more positive than C. What do I mean?
There is a potential difference.
What I mean is, okay, now you see, supposing this potential is say 2 volts and this is 0 volts. Then this is more positive than this. Correct? Hello? Hello? Supposing this point is 4 volts and this point is 2 volts. Again, this is more positive than this. Correct now?
Yes.
Now, supposing this is minus 3 volts, this point. Okay? And this point is minus 4 volts. This point is minus 4 volts, this point is minus 3 volts. Now, is this more positive than this?
It will still be more positive.
It will still be more positive now? Hello?
Yes, sir.
Correct?
Yes.
3 is minus 3 is more positive. This is what I meant. Now, you should have this clarity. When you say forward bias, usually, when you see the diagram like this for forward bias, so you always think, the voltage source should be like this. That is not the case. What we mean by forward biasing is this should be more positive than this. This voltage can be negative with respect to some common reference. Okay, but with the same reference, this should be this voltage should be such that this is more positive than this. I hope I have made the point clear.
Yes.
That is point number 1. Now, let me tell you one more point here. See, one more point. Okay. Now, I will have a voltage source. I will have a voltage source like this, and like this. So, say this is 10 volts. This is R and R. Okay, this is R and R, and this is 10 volts. So what will be this voltage with respect to this point?
5 volts.
Clear? This is 5 volts. Hello, are you with me?
Yes, sir.
Okay, now that is 5 volts. Okay, now I am going to connect, say, I am going to connect a resistor R1 to this. I am going to connect a resistance R1 to this. Okay, now when I connect a resistor R1 to this, what will be this voltage? See, now you see, if you want to really answer properly, you must start answering in my class. Use signs and answer. Don't speculate. Come on. What will be this voltage?
Sir,
Huh?
since the other 2 points are at same potential, sir, we'll connect them, sir.
I am just asking you what is the voltage here. You tell me the value. This voltage V, say if I call this point as A, okay? If I call this point as A, VA is equal to what? You just tell me in terms of whatever I give. See, you have solved very big problems, right? Very big numericals. This is a numerical which I have given you, which I usually give it for the 10th standard students when I teach electricity, and for you also. Come on. 2 poor students. Okay. Now see here. VA will be what? See, this point and this point are same, and this point and this point are at the common points. No? Hello? So this resistor is coming in parallel with this resistance. Isn't it? It is coming in parallel with this resistance and in series with this. So therefore, the current that will flow here, this current I1 that will flow here, what will be this current that I1 will flow here? It will be 10 volts divided by R plus R parallel R1. Correct? Hello? This is the current I1 that is flowing here. That is, this current is I1. Okay? Now, if this current is I1, okay, then what will be this voltage? VA.
It will be V 10 volts minus the drop across the other resistor.
Yes. So, therefore, VA is equal to 10 volts minus I1 into R. That is drop across this. Understood, students? Okay? So like that you have to calculate. Okay? Hello?
Yes, sir. Yes, sir. Yes.
Now, see, just imagine. Supposing I give this as say 5K, and this is 5K, and this is also 5K. Right? I give all these three as 5K. Then, what will be the voltage PA? So, you will calculate I1 here, 10 divided by 5 plus 5 parallel 5 will be 2.5. So this will be 10 divided by 7.5. Hello, I hope I am with you.
Yes, sir.
And you are with me. So this becomes 4 by 3 amperes. Correct?
Yes, sir.
I1 is 4 by 3 amperes. So this will be 10 minus 4 by 3 amperes into R, 5K. So this becomes 10 minus 4 5 is 20, 20 divided by 3, approximately 6.6 or something. So this will be 10 minus 6.6 will be what? Approximately 3.4 volts. Correct? So the moment you connect this voltage will not be 5 volts, it will be 3.5 volts. Because this is loading this circuit. Got it?
Correct, sir. Yes.
Now, why I am giving you this example to all of you, you will understand this. I hope all of you understood this.
Yes, sir.
See, your examination will revolve around such things. It is not like, what is given in the textbook, they are not going to ask you those things for the competitive examinations. Okay, so therefore, you see, if you are attempting high intensity examinations, then you better be prepared properly. So, students, what I am trying to tell you, supposing I give a voltage supply like this. Okay, there is a voltage supply. Say this is some R1 and R2, and if I connect this point to this and this point to this, okay, hello, is it forward biased? Hello? It is forward biased, isn't it? So this is positive, and with respect to this voltage is higher than this. With respect to this voltage, it is forward biased. Correct now?
Yes.
But you see, how much current will flow here? That is important. Now, what I mean by forward biasing is, it is not only the question of the voltage difference. It's not only question of this should be higher than this. So, sufficient current must be able to flow in this circuit. Okay, then only this depletion layer will collapse. Otherwise, it will not collapse. So, forward biasing means this should be at a higher potential than this, and sufficient current should be able to flow. So, if you connect something like this, whether sufficient current will flow like this or will depend upon the values of these resistors. Keep this in mind. Okay? Hello? Okay, fine. Please learn properly. Don't worry about examinations and all, because your future will depend upon the quality of the textbooks that you are going to read in your engineering colleges or medical colleges. Quality, and those quality textbooks, they will take such things as trivial. They presume that you are mahir in all this, and they will write the textbooks. So you should be able to digest that. So if you learn at this level very deeply, profoundly, then your next level of education will be fantastic. You will become great professionals, very useful citizens of this country. Fine. So that is what I have mentioned here. So they should be at higher potential than this, and this voltage source must be this, sufficient current must be able to flow through this. Okay, that being the first one. Now let's talk something else. Okay, right here. Okay, so this is P and N. So this is positive and this is negative. That is, this is more positive than this. So when we write here plus and minus, it means this is more positive than this. That is the meaning of this. That doesn't mean this is positive voltage and negative voltage. See, when we write a resistor like this, current is flowing here. See, when we write here plus minus, that means this end is more positive with respect to this. This doesn't mean this potential is negative. Okay. Now what happens here? So because of this positive voltage here, these holes, right? See, there is depletion layer here. Remember, there is depletion layer here, and we have had enough discussion on the depletion layer. Correct? So this depletion layer consists of what? Consists of what? What does it consist of? Immobile charge carriers. Correct? Immobile charge carriers. That is the most important thing that you have to understand. Okay? That's the most important thing that you have to understand. This is the depletion. Now, what are these? What are these immobile charge carriers? That means this is what? This is what basically this was the trivalent impurity. Trivalent impurity atom. Now that trivalent impurity atom that was put into the semiconductor, it had a hole, and that hole now has been filled up by an electron that has come from here. And similarly, here you had a pentavalent substance, pentavalent impurity. Here you have trivalent impurity. This already had an electron. This electron is now gone. Okay, and therefore this has become ions. But these ions now have their respective charges were trapped, and therefore they become immobile charge carriers. Immobile. Okay, they cannot carry any more charge, and that is the quality of this depletion. Now, when you make this more positive than this, okay, so what happens to the holes? There are other holes here, correct? Holes belonging to the semiconductor, and also holes belonging to the what? The dopant that we have used. So now these holes, because of this plus charge, they will be pushed towards the junction. That is one way to look at it, because they will be repelled, because this is positive. Second thing is these holes will get energized. That is, this voltage source will provide energy, and if these holes absorb this energy, they will get energized. Okay? Hello?
Yes.
So these energized holes, what they will do? See here, this was simply an atom, trivalent atom. This has captured an electron. But this hole, when it comes here, this has got very high energy. It will take away this electron from this. So therefore, it will convert this immobile charge carrier to mobile charge carrier. Got it?
Can you repeat?
What should I repeat?
Sir, how it becomes mobile?
Yeah, see, you are absent for yesterday's class. It is very, very critical, and you have not seen the video also, Mr. Adil.
Like there was network.
See, that's the problem. I have taken almost 1 hour to explain that. Okay, it's very, very critical. 1 hour. So these were immobile charge carriers. Why they were immobile charge carriers? Because this had a trapped an electron here. Okay, that electron was trapped. That is why I am showing it by minus sign. Now, when a highly energized hole comes near this electron is pulled by this hole. And therefore, this which was hitherto an immobile charge carrier now has become a mobile charge carrier. Got it? And when you knock off the mobile charge carriers like this, make them mobile, immobile to mobile, then this depletion layer will reduce in its size. Got it? So here, as I told you, this immobile charge carrier will now become mobile. So depletion layer is mainly because of the immobile charge carriers around the junction. Got it? And now when you knock off this immobile, the depletion layer will starts decreasing. Depletion layer starts decreasing means the potential energy barrier will also start decreasing. Okay? And that is precisely what happens when you forward bias it. So eventually, when this potential, okay, so now I will draw something like this. I draw something like this to make things simple. Okay, eventually, when you make this potential, see, I am increasing this potential from 0 to V. When the potential here, this is P and N, when this potential is something like around 0.1 volts. When this potential here with respect to this, I am taking this as a reference, is something around 0.1 volts, okay, then this depletion layer, its former width was so much, now its width has become only so much, okay, and as we increase this voltage, 0.2 volts, 0.3 volts, this depletion width goes on decreasing, and finally, if it is silicon, then this voltage, the potential difference here is 0.7 volts, this depletion layer will vanish. Why it will vanish? All the immobile charge carriers have now become mobile. Is that clear?
Yes, sir.
Yes, sir.
And as a consequence, the depletion layer is gone. If the depletion layer is gone, then what happens?
Electric field is gone.
What happens?
Electric field is gone.
Electric field is gone. Okay. Then what happens?
Potential barrier is gone.
Potential barrier is also gone. Good. I told both these things. Then what happens?
So it will become like a normal conductor.
Yes, it will become like a normal. No, it will not become a normal conductor. Okay, depletion layer is gone. I'll tell you why. Depletion layer is gone. Now these majority charges can easily diffuse to the N, and from the electrons from N can easily diffuse. Okay, the diffusion current now goes unhindered. Got it?
The diffusion current goes
Unhindered. See, the difference is this. Say at instant of time t is equal to 0. Assume that 1000 holes came to this junction. Then this 1000 holes will now start moving. That is, this 1000 holes will start moving, and new 1000 holes will come here. So that means now holes are coming and moving. Formerly what was happening? Holes were coming, and if they try to move, they were absorbed by the other end.
Yes, it is.
Okay, now the diffusion current doesn't stop, it continues to flow. The diffusion current continues to flow. That is, the holes will move like this, the free electrons will move like this. Yes, there is combination, recombination, etc. takes place, but there is net flow of charge across the junction. There is net flow of charge across the junction. See, formerly when it was unbiased, under thermal equilibrium condition, the net current was 0. But here, the net current is not equal to 0. It is due to the diffusion of charges. In normal conductor, the current is mainly because of the drift current. Here it is the diffusion current. That is an important difference. Got it?
Sir, here there is diffusion and drift both.
Wait a minute. I am talking about this point. At this junction, there is only diffusion current. Clear? Due to majority charge. Diffusion current due to majority charges at this point. Okay? Now, at this point, if you come to this point, then the current here is mainly drift current. This point and this point. The current is mainly drift current. So, what I am trying to say to you, as I told you, yes, there are two components of current here. One is drift current and diffusion current. When you come near the junction, it is mainly the diffusion current, but when you go near the ends, it will become drift current. Okay? Yes, here you see holes are traveling, but you have got a conductor. You can see a conductor. Here the current is conduction current. The conduction in the outside world is conduction current, but the current inside is diffusion current. But here you will find mainly diff current, here it will be mainly diffusion current, in between it is combination of both. Correct?
Yes, sir, I see.
I hope you are getting convinced. You are getting convinced. Okay? And you see, these are all the mechanisms that you have to learn in this chapter. Right? Okay. That is precisely what I wanted to explain to you. So, that is what happens when you forward bias the junction. Okay? Right. And as far as this side is concerned, whatever happened on this side, the same thing will happen on this side also. Okay. This is about the forward bias. Clear? Shall I proceed?
Yes, sir.
Right. Now coming to the reverse bias. So what is reverse biasing? Okay. Well, reverse biasing, as you know, this is P and this is N, and this will become more positive than this. Right? This is going to become more positive than this. Okay. Now, as a consequence, what happens? The holes here, see there is depletion layer here. The holes here are majority carriers. They are pulled this side, and here the electrons are majority carriers. They will be pulled away from the junction. Correct?
Yes, sir.
They are pulled. The majority carriers are pulled away from the junction. But the minority carriers, what are the minority carriers here? Electrons. What are the minority carriers here? Holes. The minority carriers are pushed towards the junction. Correct?
Yes, sir.
And as far as the depletion layer is concerned, this point of the depletion layer will increase. You remember we discussed this. This point of the depletion layer will increase if the concentration of the minority carriers at this point increases. See, you remember with the increase in temperature, the depletion layer width will increase. We discussed it yesterday.
Yes, sir, I see.
Why? Because as the temperature increases, the minority charge carriers will increase, and this point of the depletion layer is affected by the increase in the minority charge concentration. And because of this negative, because this is negative, this is less positive than this. Therefore, the minority charges are pushed towards this point, and therefore the depletion width will start increasing. Clear? Depletion region starts increasing means what? The potential energy barrier curve will also increase. Potential energy barrier curve increases means what? It is more difficult for a hole to cross from here. Similarly, it is more difficult for a free electron to cross over to this. Okay? So therefore, literally no current will flow through the junction. Correct?
Yes, sir.
However, there is one current that will flow. What is it? Now you see, the minority charges here, the minority charges here. The minority charge here is what? Electron. The minority charge here is what? The hole. Now these holes are, because of this positive plate, these holes get more energy. These electrons get more energy. And therefore, these energies of this keeps increasing, and therefore some of these molecules, some of these charges, some of this means the electrons here and the holes here, minority charges, they will get more energy and they can still overcome the potential energy barrier and move from here to there. So, what I am trying to tell you here is, under reverse bias condition, there is a diffusion of the minority charges. Under reverse bias condition, there is diffusion of the minority charges. Forward bias condition, there is diffusion, unhindered diffusion of the majority carriers. Here it is minority charge carriers that can diffuse. Minority charge concentration is very less, but still it is diffusing and there is going to be current here. Correct?
So it is going to be current inside the semiconductor. How will it be the circuits?
What is your question, please?
So there is diffusion of things.
Huh.
How will it flow through the circuits?
How it flows through the circuit, I will explain. I will explain. Good, yeah, I like this. I was about to explain this, you asked that question. I am very happy. Good. Okay. So,
So if it is opposing, then maybe less current.
see, so one student asked one question. Is your question related to that question or something else, Mr. Abhinav? Let me
Related to that only, sir, if you are placing in this condition, then it will be very less current that will flow.
very less current. I told you, no, this will be in microamperes. It will be in microamperes. Now you see, this positive plate, it will electron current. The electron current is like this because the conventional current will flow like this, but it is the electrons which are coming out like this. That you understand? Hello? I hope you understood that.
Yes, sir.
So here you see, if an electron is pulled like this, okay, so that means now from this substrate you are pulling an electron. That means you are going to create a hole. Got it?
Yes, sir.
And here you are injecting an electron. So you are injecting an electron and you are injecting a hole here. Do you agree? One electron comes out of this, one hole is created here, one electron enters this, one electron gets into the system. Correct?
Yes.
Now what is happening here? In forward bias, see, I am showing it as forward bias. So now the hole is going to move like this, correct? And the electron is moving like this, correct?
Yes.
So this hole was supplied by this battery, and this electron was also supplied by this battery. Agreed?
Yes, sir. Yes.
So this very electron which was supplied by the battery will travel like this and return back to the battery. And this very electron which was pulled like this will go like this, and again it will come back like this. So therefore, whatever was the concentration of the holes and the charges before this battery was connected will remain the same, because this battery is supplying the electrons from external world.
Yes.
So therefore, the current here is mainly conduction current, but the current near the junction is mainly diffusion. This is for forward bias condition.
Yes, sir.
Now, is that clear to everybody? If you have questions, ask.
Reverse bias.
Okay, now let's go to the reverse bias. Aram se understand that this is a very beautiful subject. Whatever science, logic, skill you have got, you put it to use and understand semiconductors. It is a revision of entire physics in a way. Now in reverse bias condition. Okay, there is P and N depletion layer. Now this is more positive than this. So what did I tell you? The holes are going to be pulled. The holes are going to be pulled on this side, and the electrons are going to be pulled on this side. Correct? That's precisely what I have told. Hello.
Yes. Yes.
Now what is going to happen here? What is going to happen? Again, you see, you have connected the positive terminal of the battery. That is what is forward reverse biasing. Hello?
Yes.
So here, whatever electron was pulled by this side, it will go to the battery. It will go to the battery, and this battery will send that electron here, and this hole will come here. Okay, this hole will come here, and this hole, as it comes here, this electron will absorb this. Understood? Understood. So therefore now this is there. Now you see an electron here, and a hole here. This will now cross over the junction, and it is because of this diffusion of the minority carriers you have got reverse saturation current. Reverse saturation current. It will be very, very small. It will be in microamperes. Got it?
So the diffusion current will be microamperes.
Diffusion current will be microamperes. See, this current is diffusion current here. And the current here is diffusion. The magnitude of the current is something. The magnitude of this current, magnitude of this current, magnitude of this current must be same. Magnitude of the current at any point is same. Only thing is the components will be different. Here the main component will be diffusion. Here the main component will be drift. Here the main component will be drift. Here in between, it is combination of both.
Yes, sir.
But the total current is same everywhere. It cannot be different at different points.
Yes, sir.
That is the basics.
Yes.
Because this is a series circuit. Okay? This is precisely what happens in a reverse circuit.
The current, sir, the currents are in microamperes and that magnitude, sir. Can't we ignore them, sir?
Why should you
Compared to 10 amperes or 20.
Hey, wait a minute. Don't start assuming. Don't start assuming. It is in microamperes. What is your problem? What is your problem? It is in microamperes. Let it be there. Why should you ignore it? Why should you ignore it?
Sir, but there will be.
Why should you ignore it? Why should Why should you ignore it? What is the necessity to ignore it? See, you have to ignore it in the situation, man. That is not a thumb rule. Oh, something is small means you ignore it. See, when you are a small boy, your parents ignored and went away. See, it is not like that. You have to understand the significance of that. Don't simply assume, oh, it is small, so we should ignore it. See, in a particular numerical, if you are solving, if supposing, say, in the numerator or denominator, you have a large number and a small number, so then, looking at the situation, the example, you will ignore the smaller number. That's it. Now, here, nothing like that. Now, understand this. The current will be very, very small, and it is mainly because of the minority charge carriers. And the current is not dependent on the potential difference. The reverse bias current is not dependent upon the potential difference. It is dependent upon how many minority charges are there, and the minority charges depend upon the temperature. So therefore, the reverse bias current is mainly dependent on the temperature, the ambient temperature, and the temperature of the device. Okay, shall I proceed?
Yes.
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 See, you should learn this like a beautiful story, man. Okay, don't learn it in discrete things. I am connecting everything so nicely for all of you. Okay, but keep your eye on the depletion there. Okay. So now, whatever I have written there, I have summarized it. So I think you can read this. This is visible to all of you.
Yes, sir.
Right. I hope you have read that. Okay. If you have finished reading, you tell me you have finished reading, and if you have any doubt, you ask. If there is no doubt, let me proceed. Shall I proceed?
Yes, sir.
Everybody, read it and tell me if you have any doubt. Hello, did everybody read this?
Sir,
Huh.
so here they're telling that minority carriers will be drifted.
Huh. They are mainly telling minority carriers will be drifted at this point. Here it is diffusion. That's precisely what I have put. Good observation. Got it? And see, it is of the order of microamperes. Okay. Huh. Now, here I am coming to one more important point. See, now as I told you here, this. Now, can somebody tell me why this resistor is added? Can somebody tell me why this green color is this resistor is added here?
To maintain voltage across the time.
Come on, think and answer. Why? What is the purpose of resistor? The purpose of the resistor is to limit the current. Understand? Limit the current. What do you mean by limit the current? See, now I have a battery, and if I put a resistor, okay. Now you see, if I connect an external load to this RE, okay, and if I vary this RE, that is RL I am going to vary from 0 to say 100 k. Okay. Now, what is the purpose of this R here? The purpose of the R here is that if I make this RL equal to 0, the current that will flow in this wire will not be more than V by R. So, the current is limited to V by R. Got it? So, accidentally if you turn this to 0, then this voltage source will only give you so much current. If you don't use this resistor, then if this load resistance becomes 0, then you will have infinite current flowing here, and this will be killed. That is why this resistor is added as to limit the current. Okay?
Yes.
Now, if I tell you, oh, this will be asked in examination, then you will take it in your head. Don't do like that. There is a purpose. Just not for examination, for your future also, you need to understand these things correctly. Right? Okay, so that is added like this. Now, you see here, there are some important things. So now, you see in both these circuits, in the reverse bias, see in the forward bias, I will make this variable. So I will vary this from 0 to say some voltage V1. So what happens? So as I increase the voltage from 0 to 0.7 volts, the barrier is still, the depletion layer is still there, and at 0.7 volts for silicon, the barrier will, the depletion layer will vanish, the potential energy barrier will collapse. Correct?
Yes, sir.
And there afterwards, after 0.7 volts, if you increase the voltage, then the current will flow depending upon the value of this resistor. Correct?
Yes, sir.
Fine. And that is one aspect of this. Okay. So therefore, the current will start increasing as you increase the voltage beyond 0.7 volts for silicon. Now, the same thing if I do it for this. What happens? So, as I increase this voltage, the reverse saturation current is very small, microamperes. The reverse saturation current is very small, microamperes. So, microampere current will be flowing through this. Okay, and what will be the drop here? The drop here will be whatever microampere current is flowing into R. That will be the drop. The remaining voltage will be across. This. Okay, now you see, you have studied bulb. Okay, bulb, right? So to a bulb, you have, say, suppose you connect a resistor and a battery. Okay, so this bulb has got, say, some wattage, say some say 10 volts. Okay, so as you increase this voltage, the current starts increasing. And when the current in this is such that that is the resistance of this bulb, if you supposing it is R, then I square R. I square R, if this is equal to 10 watts, the bulb will glow to its maximum capacity. Correct?
Yes, sir.
Now, if you measure the voltage between the bulb at this point, this voltage across the bulb into the current flowing is nothing but what? The power dissipated in the bulb. Correct?
Yes.
Now, here instead of the bulb, you have got this semiconductor material. So here, as you are increasing the voltage, the current is not increasing. The reverse saturation current is fixed, small current, but the voltage across this is increasing. As the voltage across the diode is increasing, so the voltage across the diode into the current through the diode. Current through the diode is constant, but the voltage is increasing. So the power dissipated. The power dissipated in this diode is increasing. You know what is power dissipation? So here you see, in the bulb also the power is dissipated. What happens when the power is dissipated? Yes. First thing is, this bulb is heated. Temperature will increase. Temperature still increases, it becomes incandescent. And then it starts emitting light. I hope all of you know this phenomena.
Yes, sir. Yes, sir.
So here, the voltage increases, the dissipation here will increase, and the temperature will increase. Temperature of the diode will increase. Got it?
Yes, sir.
Dissipation is in the form of heat also.
If you speak so slowly, I can't hear, gentlemen. Some louder and matada.
So that dissipation is only in the form of heat or any other forms?
Dissipation is only in the form of heat yearly. What other way it can dissipate? Heat only and temperature will increase. So if temperature increases here, this is what happens. The more bonds will break, the minority charge carriers will increase. So slowly the reverse saturation. So what happens? The minority charge carrier concentration will increase, and then there is something that is going to happen. What is going to happen? Okay. So here you see there is something called as breakdown. There is something called as breakdown. Okay. What is that breakdown? Okay. Breakdown means here this current through this junction is supposed to be controlled. Now it becomes uncontrolled. It becomes uncontrolled. Okay, because of the temperature. Okay, what is that uncontrolled thing that happened there? You have studied this now in the college. You can tell me quickly so that I can proceed. What is that uncontrolled? Uncontrolled means, you see now here, the minority charges will gain more energy. Temperature has increased, so more number of minority carriers are there. So one thing is, these minority charge carriers will have a lot of kinetic energy. They will now start to go and they will start splitting the bonds. See, the bonds are split because of temperature is one issue. The bonds are split because of temperature is one issue. But some other molecule will come and hit it, and then the bonds will break. That is another thing. See, you see in Himalayas and the snow-driven mountains, there is something called avalanche. One boulder starts coming down, snow boulder, it will hit one more boulder, and that boulder will split into two, and that will hit something else, and so there is chain of such events, collisions that take place, and you will see a whole mountain as if it is coming. Avalanche.
Yes, sir.
Okay, so avalanche phenomena can take place within the diode, and the diode can get destroyed permanently. That is one thing. Hello, are you with me?
Yes.
Yes, Yes, Adil, you wanted to ask something?
Destroyed that in as and what will happen? Is it
Destroyed, khatam. Halgi barsu.
like will it break or something?
Break, no, it will smell smelling. It will burn, man.
Okay.
It will burn off. It will burn off. Okay, it will fuse. Okay, so that is one type of phenomenon. There is, now there is one more thing. There is one more phenomena that takes place. Okay, so now here is something like this, Now when you make a diode, you see how you have made a diode. I think all of you know. You create a P type and you create a N type, and you make a metallurgical union of both. Okay. Now the percentage of dopant that you add. the percentage of dopant that you add. If you are using dopant here, and if the concentration of the dopant is very large, then we say it is heavily doped. Otherwise, we say it is mildly doped or lightly doped. I hope you know this concept. Heavily doped, mild doped, and this two. Now you see, if you have doped it very heavily, okay, then the depletion layer will be very, very small. Yesterday we have discussed this.
Yes, sir.
Depletion layer will be very, very narrow. Okay, and therefore, if you are doped it very heavily, the depletion layer will be very narrow. And as a consequence, when you reverse bias this, then what happens here is a different phenomena. And if you are heavily doped, what happens here is a different phenomena. Okay, so what I am trying to tell you is, one is the diode will break down because of avalanche. Just now I explained. Another breakdown is called, avalanche phenomena. Other breakdown is called Zener breakdown. Okay. Now, Zener breakdown will take place because the electric field intensity is increasing. If the electric field intensity increases, okay, then what happens? The minority charges will get more energy, and they can easily cross over the depletion layer and go to the other end. Okay, and it can go in such a manner that the depletion layer is overcome. I'll explain that in detail with some proper diagram. So that is avalanche breakdown. So therefore, you have to exercise control over this when you are doing reverse bias. So I'll explain these two phenomena to you. Right. So I hope you can read that. In reverse bias, the current is very small and nearly constant, with bias termed as reverse saturation current. However, interesting behavior results in some special cases, that is breakdown in a diode, Zener breakdown and avalanche breakdown. Okay, I made it very sankshipta, it's a big theory, but anyway, in brief I'll explain. Avalanche breakdown occurs due to a rapid collision of electrons with other atoms. Zener breakdown occurs due to high electric field. Zener breakdown is a controlled version of avalanche breakdown and in a modified PN junction. Basic difference between the two I have. Now, avalanche breakdown. This type of breakdown occurs in the presence of high electric field. When you apply high electric field, a reverse bias condition, electrons start gaining high kinetic energy. These electrons start breaking other covalent bonds and start creating more coelectron pairs. These pairs start crossing the depletion layer and contribute to high reverse bias current. The breaking of the bond is irreversible process, and the PN junction is completely defined after the avalanche breakdown. I hope I have explained this, and these words are quite concise, precise, and to the point.
Yes.
Zener breakdown. Zener breakdown is controlled way of creating PN junction diodes. The PN junction has to be heavily doped so that the electrons in the valence band of the p-type region can easily jump the conduction band of the n-type. The temporary breakdown occurs due to high electric field. As it does not contribute to chain reaction, the effects of Zener breakdown is temporary. That means you increase the voltage, there is Zener breakdown, okay, and then what happens to the Zener breakdown? I'll explain. And then you reduce the voltage, the diode will come back to its original condition. But in avalanche breakdown, if you increase the voltage, avalanche breakdown happens. Now, if you decrease the voltage, then Zener is already killed, the diode is already killed, and you can do nothing out of it. But in Zener, you increase the voltage, Zener breakdown will take place. Then, if you decrease the voltage, the diode will once again become alive. It will not get permanent, it will not get destroyed. Correct?
Yes.
Now, so this is just a schematic of this. So here you see, when the reverse bias voltage, see this reverse bias voltage is at this point, then what happens? This is the curve. This is the curve of what? This is current versus the voltage across the diode. So as the voltage across the reverse voltage across the diode is increased, okay, at this voltage Zener breakdown takes place. That means now here you see this curve is slightly like this. Okay, that means for a small increase in voltage, there is a large change in current. For a small increase in voltage, there is a large change in current. Okay, after it crosses this point. But in avalanche diode, well, it breaks down. That means it's the permanent vector. This is the basic difference between the two. I hope it is clear. Huh. Okay. Okay. So now I just put these points here. Forward bias, reverse bias. What are all the differences? Whatever I explained, it is here. Only this graph I have to explain. I will explain to you. Please read this and try to understand. Whatever doubts you have, you ask. I will explain. Okay, wait. I'll just give you another 3 minutes. Let everybody read. We'll start the question and sessions. Okay. I hope everybody have read this. Hello.
Yes, sir.
Yes, sir.
So this point, I think I have explained. This also I have explained. Now coming to this graph. Arun, I will answer your question. Let me first explain this. See, here as you can see, the what is this graph for? This graph is for the diode which is forward biased.
Yes, sir.
Correct? The diode which is forward biased. Right? So this voltage here they have written it as VD. VD is what? This voltage. And
Yes.
ID is what? This current. ID. Okay, this current is ID. And here they have written it as IF. IF means forward current. Okay, that's the meaning. Okay. Now, as you increase this voltage, okay, so here you see the current will slowly increase. Okay, at this point, after this point, the current will increase like this. Did you observe this?
Yes.
Now, you will explain me this part of the curve. Why this part of the curve is like this? This part of the curve. Why is it like this? Come on, use whatever I have told you.
Sir,
Huh.
before the voltage has reached that voltage, sir, particular voltage, there is still some depletion region on this.
Excellent, good, brilliant point. So till this point, the depletion layer is still existing. Depletion layer is slowly breaking. Okay, slowly becoming narrower and narrower. That is why the current is slowly increasing. Once it reaches this voltage called knee voltage, or this is called cut-in voltage. Cut-in voltage. For silicon it is 0.7, for germanium it is 0.3. Therefore, this will be like that. Once that is reduced, then the current will increase. In an ideal diode, it will be like this. But in a real diode, it is like this. Correct?
Yes, sir.
Wait. So therefore now this curve is like this. That means now you see what is this? This is delta I. What is this? This is delta VD. So delta VD upon delta I gives you what? The voltage upon current gives you resistance. This is called forward resistance of the diode. Right? There is some opposition. There is some opposition to the flow of the diffusion current, and that is modeled by this forward resistance. Got it? That is given by this.
Sir, won't that resistance be same as that rho L by A? Sir?
No, it is not rho L by A. Rho L by A is for the metal, man. Metal conductor. Metal conductor. Here the currents are because of the diffusion of the charges.
Yes.
Diffusion of the charges. See, as far as diffusion of the charges. So here the graph is very clear. The current has increased by delta I for the corresponding change in delta V. So therefore, we are just taking this ratio and we are calling it by the name resistance.
Yes, sir.
See, the very definition of resistance is like that. Okay. See, now you change the voltage. See, I'll tell you. Across, see, what is the concept of resistance? Say, supposing there is a device. Okay. Now, if you change the voltage across this way, delta V. Okay. Then there is a corresponding change in the current. Hello, are you with me?
Yes, sir.
Now, you see, if you change the voltage across this field delta V and the current changes, the change in the current is equal to infinity. The change in the current is infinity. Then that means this is offering no resistance. Hello?
Yes, sir.
But if there is a finite change in the current for a finite change in the voltage, then we say this is offering opposition to the flow of current, and that we conceptualize it and call it as resistance.
Yes.
Correct? So now going by that, I measure the change in the voltage across and the current through. I take the ratio. I get a number. That number I said it is the opposition to the flow of current across the junction.
Yes, sir.
And that is RF in the forward. Now similarly I will do it here. Here also, who will explain this curve, this part of the curve?
Sir, that part I don't like.
Sir, the depletion ratio increases so much that no advantage can.
Big. Aram se understand. Aram se visualize. You can answer Arun. Aram se, don't be. So visualize. So this is the PN junction diode. Now this is more positive than this. Okay. Now this is more positive. So the minority charges are crossing. Correct? Hello.
Yes, sir.
Minority charges are crossing. Hello, Arun.
Yes, sir.
So as you increase this voltage, so you are pushing the minority charges. And initially the minority charge crossover diffusion current is controlled by this voltage or the electric field, external electric field. Got it? Initially.
Yes.
Initially it is controlled. But as you increase this voltage, whatever, because the minority charges are very, very less, concentration is very, very less. So when most of the minority charges are already moving here, whatever minority charges are here, they already are moving. Now if the voltage increases, if there are some more minority charges, it would have also moved. But all the minority charges are exhausted, they are already set into motion. Okay, there is no more minority charges which are still sitting and say, okay, I will move later on. All of them have started moving. So that means all the minority charges are already in motion. There is no more minority charges in excess which will increase the current, and that means it is saturated. That is why it is called as reverse saturation current. So up to this point, there is increase in the minority charges that takes part in the diffusion. There is increase in the minority charges that take part in the diffusion. After this point, all the minority charges on either side have participated, and therefore there is no more further increase in the reverse saturation. Okay, and therefore it remains constant.
Yes.
Got it? Now here a figure of merit, delta V by delta I, we get it as reverse resistance. This is forward resistance, and this is of the order of 10 to the power of 6 ohms, megaohms. Okay?
Yes, sir.
Now, the knee voltage, cut-in voltage or knee voltage, for germanium it is 0.3, this is 0.7, I have already explained. Breakdown voltage, this is approximate figure, sir. For germanium it is 25, for silicon it is 35 volts. Special point, RF upon Ri for germanium is 10 to the power of 3 to 1, RF upon Ri for silicon is 10 to the power of 4 is to 1. Remember these things. Okay?
Yes, sir.
Sir.
Now quickly. Any doubt? Okay. Now quickly solve this problem. When the resistance of PN junction diode decreases when forward biased and increases when reverse biased, right? Okay. Take 2 minutes time and don't ask. I will go drink water and come. Write the answer in your notebook and keep it ready. Yes. Who will answer? Hello. Hello, are you there?
Yes, sir.
Answer it. Hello, everybody try to answer. Now you see students, if you are students of physics, then you know how to answer. If you are not students of physics, you cannot answer this. Okay, now listen very carefully. What is the concept of resistance? Opposition to the flow of current through the device, correct?
Yes, sir.
So now the resistance of a PN diode decreases in forward bias. So that means when you forward bias it, the current has some opposition. Okay, that opposition is the resistance in the forward bias condition, correct? And what is the opposition?
Yes, sir.
What is the cause for the opposition? It is in terms of what? It is the potential energy barrier, isn't it? That is across the junction. So it is the potential energy barrier across the junction that is opposing the flow of forward current, correct?
Yes, sir.
So when you increase the forward bias, this potential energy barrier will decrease. Why? Because the depletion layer is also decreasing, and therefore as the voltage increases, the potential energy barrier will start decreasing, and therefore what happens? The resistance will also decrease. The resistance to the flow of current will decrease. Okay. In the reverse bias condition, the depletion layer is increasing, width is increasing, and the potential energy barrier is also increasing, and therefore the opposition to the flow of the reverse current is also increasing in the reverse bias condition. See, you should conceptualize it like that. Your search engine should not start, oh, what is the definition of this? Then you will not do any physics. You cannot remember 1,000, 10,000 definitions like that. Okay? Hello?
Yes.
Yes, sir. Who's sir? Okay, done. Okay, now answer the next question. See, you should answer it to physics. When an ideal diode, what is an ideal diode? What is an ideal diode?
It should have zero resistance, sir.
ಏನಂದ್ರೆ zero resistance ಅಂದ್ರೆ Arey yaar, come on.
Potential bias.
See, now, you conceptualize that. Physics is full of concepts. Here.
Even after the depletion, there is constant. There is no.
See, now you are at circuit level. Okay, you should talk now at the circuit level. See, what is the characteristic of a real diode? This is the characteristic of a real diode. Correct now?
Yes, sir.
Now, in an ideal diode, what happens? The characteristic of an ideal diode will be like this. Okay, instantly it will have a forward current and reverse current is zero. The characteristic will be like this.
Sure.
Understand? This is the characteristic of an ideal diode. The characteristic of sorry. There you see, I have taken the cut-in voltage here and I have shown it like this. I have shown you cut-in voltage and I have shown it like this. Well, even the cut-in voltage will be very, very less, almost equal to 0 or 0. Okay? That is the characteristic of an ideal diode. So, an ideal diode is one, which has this characteristics. Okay?
Within cutting voltage, what will be the link?
See, idealized diode is such that the cut-in voltage is almost 0. Of course, let me tell you very clearly to all of you. Now you go by what is given in the NCERT book. See, in some lessons, some school of thought, they call this as ideal diode. That is cut-in voltage. And in some school of thought, they take the cut-in voltage as 0 and do this. But this line is for vertical and this line, this reverse saturation current is horizontal. That is for truth. Only thing is, this is the issue. Okay? So, but go by this. What is given in NCERT book, go by that. I go by this. The cut-in voltage is 0 and as soon as you connect it, it will be like this. That is the ideal. Got it? Okay. So the characteristic should be like this. Draw the output waveform across the load resistance R. So, for this input voltage, see this voltage is given as input here, right? That is, you take this as the reference point with respect to this reference, you are feeding this voltage. That is, the voltage at this point is 0 for some time and then suddenly rises to 6 volts and then stays for some time at 6 volts and then comes down to minus 6 volts, stays for some time and then once again becomes 0. I hope you understood the signal. That is given at this point with respect to this point. So,
Yes.
now as a consequence, what will happen? Solve this problem.
So in the first case, the diode is forward biased.
First case
So-
means what?
Current will flow according to
First case means
like
what?
a normal situation.
Hello, first case ಅಂದ್ರೆ ಏನು? First case ಅಂದ್ರೆ ಏನು?
Forward biased.
First case ಅಂದ್ರೆ ಏನು?
See?
ಅದನ್ನ first case ಅಂತ ಹೇಳಿದ್ಯಾ? ಏನದು first case?
So when voltage is 6 volt, positive voltage,
Okay, let me do it like this.
like anode is connected to
Okay, wait.
anode, P-type, that.
Right. So this is the voltage and this is the time. Correct? This is voltage and time. Right. So the signal that they have given is something like this.
So this is not voltage versus current graph.
This is voltage versus time, right?
Time.
Voltage versus time. And this they are told is 6 volts. Okay? Now, what happens? During this interval of time, you see this circuit here. So, here, during this interval of time, the diode is off. Correct? Because this voltage is 0 with respect to this voltage. Okay. Now, during this period, this voltage is 6 volts with respect to this one. Therefore, the diode is on. Correct? And now during this time, this voltage is negative with respect to this. Again, the diode is off. Clear? And again here, the diode is on. Okay? Hello?
Yes, sir.
Diode is on means what? For this excursion, you should treat this diode as if you should treat this diode as if it is open circuit. As if it is open circuit.
Yes.
As if it is open circuit. Okay? And then of course you have the resistor. So that means now when this voltage is there, diode is open, how much current will flow here? No current will flow. Therefore the voltage across the resistor is also, zero. Now during this transition, the voltage across the diode is on. So when the diode is on, you should treat the diode as if it is a short circuit. And what is the voltage here? It is 6 volts. It is 6 volts with respect to this. What is the current that will flow here? The current that will flow here is 6 by R. And what is the voltage across this now? No drop here. The voltage across this VR will simply equal to 6 volts. And here also the diode is off 0, 0 because the diode is off. So therefore, the diode is on only for this region and therefore the output voltage here for the input voltage that is shown here, the output voltage will simply be what? The output voltage will simply be this. 0, 6 volts. Correct? So this is how you will get the output voltage for this input voltage. Did you get it?
Yes, sir. But I get that, sir, what will be the breakdown,
What will be the?
breakdown voltage for reverse bias?
Okay. For ideal voltage it is infinite.
Infinite, right?
Infinite. Ideal type.
Okay.
Ideal means ideal condition, which is not real. Right? Okay. Good question. Now you are all beginning to learn and you please learn. See, infinite resistance when it is reverse biased. Got it? Reverse biased. Output voltage has 0 resistance and also see they have shown here 0 to 6 volts now. That means it has no cut-in voltage. Got it? See, if it had cut-in voltage, then it would be 6 volts minus 0.7 volts.
Yes.
So therefore, this is the thing that they have used. Okay.
So breakdown voltage will be
Breakdown voltage will be infinite.
Infinite.
For ideal diode, man.
How serious?
Arey yaar, why you want to bother about it now? Why you want to bother? See, it can sustain large reverse voltage. That's it. Or the reverse resistance is, the reverse saturation current is 0. The reverse resistance is infinite. Like that you should matter. That's it. Okay? See, I told you no. The ideal diode, for ideal diode, the graph is like this. Okay, this is current versus voltage.
AC resolution.
Is that? Okay. A potential barrier 0.5 volts exists across PN junction if the depletion region is 5 into 10 to the power of minus 7 volt. What is the intensity of electric field in the region? The electron with speed so and so approaches the PN junction from N side. What is the speed after it enters the P side? So this potential barrier voltage is given, width is given. So V by distance, V by L gives you the electric field, isn't it? So the electric field here will be V, 0.5 volts divided by 5 into 10 to the power of minus 7. Okay, so this becomes 10 to the power of 6 volts per minute. Okay? What is the intensity? The electron with speed of 5 into 10 to the power of 5 approaches the PN junction. So that means now the initial kinetic energy of this is half m Vi square. Vi square. Okay? The electron with speed of 5 into 10 to the power of minus 5 approaches the PN junction from N side. What will we see as it enters the P side? What will enter the P side? So this minus the drop, the potential energy lost in the depletion region. What is the potential energy barrier here? 0.5 volts. So 0.5 volts is half, okay, into the charge of the electron. The charge of the electron, isn't it? 1.6 into 10 to the power of minus 9. That is the, see, this is the kinetic energy of the electron, and this is what? This is the energy that is that the energy, the electron loses this energy because it has to overcome the potential energy barrier. Correct? And it will come out with this half m Vos.
Yes.
So, but you should know the electron speed of the, what will be its speed when it enters the P side. So this will be the equation, correct? Half will go.
So it is.
Correct, know what I have written? If I have written wrong, you should tell me. Right. Okay, let me see. Let me see what I have said. Okay, as you put it. Okay, same equation produced.
Yes.
Okay, done. Half it. So 2.7 into 10 to the power of 5. Correct. So we don't know the mass of the electron which are supposed to. I think all of you know the mass of the electron now. 9.1 into 10 to the power of minus 27 kg. Minus 27 kg. You have to put that at equals.
Yes.
Okay, done. Figure shows a diode connected to external resistance and an EMF. Assuming the barrier potential developed in the diode is 0.5 volts, obtain the value of the current in milliamperes. So the circuit is like this. the diode, and then this is the resistor, and then this is the supply. So this is 4.5 volts, and the resistance is 100 ohms. Okay. So this is the diode, kinetic external resistance, and then EMF, assuming the barrier potential. So the barrier potential is what I have here. So the barrier potential here, it is V13. So it is a 0.5 volts. Okay. So they are asking you what current in milliamps. This current in milliamps. Very simple. 4.5 volts minus 0.5 volts.
Yes.
This is 4 volts. So 4 volts, 4 volts divided by 100. Okay, it gives you the current. Gives you the current. They are asking it in milliamperes. Current in milliamperes. So current in milliamperes is what?
0.4 milliamperes.
0.4 milliamperes.
Yes.
Or 40 milliamperes.
40 milliamperes.
40 milliamperes. Multiply and divide by 10. You get 40 milliamperes.
Yes.
Okay. I hope you are getting some idea out of this. Right?
Yes.
Differentiate between Zener and avalanche breakdown. Okay. So the question is there, answer is also written here. So just read this. Okay, I have explained all this. It is written here. Clear? Hello?
Yes.
Now I am coming to the next topic, rectifiers. Okay, rectifiers. Okay, now read the two definitions. I will explain these two definitions for you. Rectifier. So one definition that you find in most of the textbooks is alternating current in an electric current which periodically reverses direction and changes its magnitude continuously with time, in contrast to direct current which flows only in one direction. Rectifier, it is a device which is used to converting alternating current into direct current. It is one of the definitions that you find in most of the textbooks. Okay, now here you see students, here what he means by alternating current is, a current which will periodically reverse its direction. Okay, something like this. It can be sinusoidal or it can be non-sinusoidal, but it should have a positive part and a negative part. So he says, well, there is current which is not one unidirectional but bidirectional. One's positive, one's negative, and a rectifier will convert this into current which is going in only one direction. I hope this definition all of you know.
Yes, sir.
And did you understand the definition? In the textbook also this definition only is given, I suppose. That is what it is. But somehow you are all wonderful students, you can get a better idea. Okay? So I would recommend you to go with this definition. But of course in the examinations, if they ask you whatever definition is given in your NCERT textbook, that definition only you must write. But for a better knowledge, I will give you this. Now read this definition. A device that converts sinusoidal voltage waveform of zero average value into another waveform, not necessarily sinusoidal, whose average value is non-zero, is called rectifier. Okay, so what I mean here is very simple. So here you see, I would have a sinusoidal signal. Well, as all of you know, this is voltage versus time, and this voltage is, say, V out sine omega t. So its average value, V average value is equal to 0, because you know, average value of this is 0. Got it?
Yes, sir.
Huh. Now, if I pass this through a device called rectifier, okay, then at the output of it, I am going to get a waveform. I am going to get a waveform which is going to have, I am going to get an output which is not necessarily a sinusoidal waveform. It can be any other thing other than sinusoidal. It can also be sinusoidal or other than it, but whose average value is non-zero. Whose average value is non-zero. That is called as a rectifier. Did you understand or did you not understand? You make it very clear. I will nicely explain it to you. Or if you want to say something about it, you can tell. So you want to waste your time, then no issues. Okay friends, see now let me do it like this. So what I will do, I will take this is a symbol for AC voltage source. This is a symbol for AC voltage source. So this is going to give out V of sine omega t. That is the waveform that is available at this point with respect to this point will be of this shape. Okay? Hello? That is it. Okay. Now what I am going to do is I am going to take this waveform, this signal, and I am going to send it through a diode. I am going to send it through a diode through a load.
Yes, sir.
So what happens? So this one, you see, this is 0 E versus V. So this is plus V naught, and this is minus V. Okay, so as you know, a diode. During this part, the diode is this more positive with respect to this during this interval of time. Agreed?
Yes, sir.
And I am considering an ideal diode. So therefore, this diode will be what? This diode will be on.
Forward bias.
This diode will be on during this extension because
Yes.
it is forward biased. So whatever is the voltage at this point, the same voltage will come here, and this is the common reference point. So therefore, this entire voltage waveform will come across this. Therefore, the voltage at the output, for this input, the voltage at the output for this input, I am telling you the voltage at the output will be what? Will be like this. Okay, for this part. Now for this part, this diode is reverse biased. So therefore, this will be open circuit. So this will be open circuited means no current will flow through this. No current will flow. Current into RL is 0. So therefore, the condition will be what? This will be flat up to this point.
Yes.
Now after this point, once again it is forward biased. So once again it will be like this. It continues. Now you correlate it with this definition. This is a sinusoidal waveform whose average value V average is equal to 0. Now what will be the average value of this signal? The average value of this signal, that is, you have to integrate the sine omega t from 0 to pi. Okay, then you are going to get this value as V naught by pi. The average value of this signal will be V naught by pi. Correct?
V naught by 2.
V naught by 2. So integration V naught sine omega t d omega t over
Omega will come out.
over 1 by pi. Okay, and this is from 0 to pi. Because 0 to this is pi to pi, it is 0. No point in integrating.
Check that 1 by 5 will not come out.
I am just integrating it. Help me for the integration. Help me for the integration. Okay. So integration of sin omega t will give you what? Cos omega. Okay. 0 to
1 by 2 pi.
Wait. 125. Correct. 1 by 2. 1 by 2. So this is minus cos omega. So this gives you minus cos t. Pi minus this will give you minus into minus will be plus. So I will get here P naught into 2 by 2 pi. 2 will be cancelled. So we get here V naught by pi. Okay? So V average value will be V naught by pi. So the average value of the input is 0. The average value of output is V naught by pi. Okay? Hello. Are you with me, all of you?
Yes.
So that means now only half of this signal is rectified. The other half is not rectified. So this type of rectification process is called half wave rectifier.
Yes.
Understand? So that is precisely what I have said. So this device is responsible for this action. I will suppose it is clear. Hello?
Yes,
Clear. Okay.
Sir, but this will like only half of the time you will be getting the supply, sir, and it will be fluctuating continuously. Sir.
Yes, let it fluctuate.
Like with
Yes.
the device of load.
Yeah, it will fluctuate, correct. So if this frequency, right now you see, you know,
It will not be good for the device that you are attaching.
no, nothing will happen. No, don't worry. No, don't worry so much. Don't worry so much. Don't worry so much. These devices are designed for million such operations. Million such operations. See your car, how many bumps it will take, how many times you brake, will it get destroyed? No, they are all designed like that. That all you don't bother, man. You see, you learn science, man. You don't think about any technology and all. You will do nothing in life. I am teaching you science, so it is not good for the device, it is bad for the device. So that all should not bother. I think this is what you are going to do. You sit with the book and start dreaming. This is not the way a student of first PUC, second PUC should behave. You first complete your graduation, learn what is there in graduation, complete your masters. Then if you want to sit and do PhD, you do PhD. For that, they will give you money for thinking like that. Right now, don't do PhD. Just learn these things. Did you understand this half wave rectifier? Hello, friends? Hello?
Yes, sir.
Yes.
Right. Okay. Now, this is one part. Shall I rub this? Okay. Now, you see, I will take a point. I will take this point as say point A. And I will take a diode like this. I will take a diode like this. Okay, I'll take it. Hello, are you with me, all of you? This is point B. From B, I will take, what is this lighting green? Hello, if you are there with me.
Yes, sir.
See, between these 2 points, I am going to connect the voltage source. V naught sine omega t. And this is R. Okay. So, what will be the waveform? Vxy. So, Vxy versus time will be this way. Correct?
Yes, sir.
Correct?
Yes.
Now, this point is the voltage across this. So, this one I will call it as x dash y dash. So, correspondingly, what will be the V x dash y dash waveform? Everybody, it is open to everyone. Please tell me. So, analyze it. So, now you see, for the first instance, that is this period, or this period. Okay, this point is positive, this point is negative. That is during this interval of time. Agreed? Hello?
Yes, sir.
So then this is more positive than this point. So this is more positive means this, see, this is more positive. Look at the sequence. This positive, come here. So this diode can become on, and the current can flow like this, the current can flow like this, the current can flow like this, the current can flow like this. So therefore, during this positive excursion, this diode and this diode will become on, and therefore the current will flow like this. The current from here will flow like this. Correct?
Yes, sir.
And these 2 diodes are off. These 2 diodes are off. Now, during this excursion, what happens? During this excursion, this is now negative, this is positive.
Yes, sir.
Okay, so therefore now the current will flow like this. See, here the current is in the same direction in both the cases, and then the current will return like this. Got it?
Yes, sir.
So in this excursion or in this excursion, the current in this RL is always from x dash y dash. So therefore, I will get the waveform across this like this.
Yes, sir.
So this is called bridge rectifier. Okay, and this type of waveform is called full wave rectifier. Understood? Now, if you perform the average value of this, the average value of this will come to 2 V naught by pi. For half wave, you have got it as V naught by pi. Here you will get it 2 V naught by pi. Again, you see, an input waveform whose average value is 0 is converted into another waveform whose average value is non-zero. Got it?
Yes, sir.
Hello, everybody there?
Yes, sir. Yes, sir.
So this is another way of getting the bridge rectification. I will discuss full wave and half wave. The comparative study I will do, but right now just understand what is half wave and full wave. Okay. Shall I continue, students?
Yes, sir.
Yes, sir.
Wait, I'll just take another 5 minutes and complete. Okay. Now here you find a transformer being used. Can you see a transformer being used? Hello?
Yes, sir.
The same circuit with the transformer being used. So why is the transformer used there?
To reduce the voltage.
To step up or step down the voltage, the transformer.
And the voltage.
What else is the purpose of the transformer here? More step down, step up is one thing. Any other reason why transformer is used?
Sir, any sudden change also? Any sudden change, sir?
In sudden change.
In the water voltage. AC supplies.
Any sudden change the sudden change in input will become sudden change in output. See, I have taught you all these things. You don't want to learn. I told you galvanic isolation. I have taught you, no? That is why we are using a transformation. See, the energy here is electrical, then the energy becomes magnetic, and then again electrical energy. So there is no physical wiring there. So there is something called as galvanic isolation. So you will be isolated from the main supply. That is the main thing. Anyway, I have explained that in detail. If you have forgotten, God save you. So that is the reason. Well, so here again I have explained the circuit. What this waveform also I have told. So this is what happens in a half wave application. Okay, same thing. So there is a concept of peak inverse voltage. So now you see, during the positive cycle, this diode is on. So the current will flow like this. Okay, no issues. But during the negative cycle, this diode has to block the voltage. That means the negative voltage will come across the diode. The reverse bias voltage will come across the diode. Correct? And this is called as peak inverse voltage. So during the reverse bias, this voltage, which voltage? This voltage, this point, minus V0. This is the inverse voltage, or the minus V0 becomes the peak inverse voltage. So here you see, the peak inverse voltage is one of the important specifications of a diode. If you go and see the diode, it has got so many specifications. Maximum forward current. Another one important specification current is the peak inverse voltage. So if you are using a diode here, the peak inverse voltage of this diode, that is, say, supposing the diode peak inverse voltage rating is 20 volts. Then V0 must be less than 20 volts. Okay, if it is more than 20 volts, the diode will break off. So peak inverse voltage. So what in this case, what is the peak inverse voltage? The peak inverse voltage will be the maximum voltage across the secondary of the diode. Okay, quite simple. Hello?
Yes, sir.
You will be using all the specifications, be careful. In full wave rectification. This is another configuration of this. I hope you know about this configuration. Hello?
Yes, sir.
What is this configuration? What is this configuration called? Any guess? ಅಲ್ಲ ಇದಕ್ಕೇನಂತಾರೆ ಆಗಲೇ ಬ್ರಿಡ್ಜ್ ತೋರಿಸಿದ್ನಲ್ಲ ಬ್ರಿಡ್ಜ್ ಈಸ್ ಆಲ್ಸೋ ಫುಲ್ ವೇವ್ ರೆಕ್ಟಿಫಿಕೇಶನ್ bridge is also full wave rectifier, but here what is this called? This is called, what is this transformer called? Hey, you have learned all these things in the college, man. That is why I am asking you.
It is a full wave.
What is this transformer? See, I have used, there was one previous, this one I used a transformer like
Step-down transformer.
You know? See, just now we had
Step-down transformer, sir.
Hello, ಈಗ half wave rectifier ಒಳಗೆ we had used this transformer. Now we are using this transformer. Correct?
Yes, sir.
What is this transformer and what is this transformer? Both are transformers. This is called center trap. Center trap transformer. You know what is center trap transformer?
Center trap, yes, sir.
What is that?
It can divide into two seconds. It is like part of two seconds.
Slowly, I will explain. See,
Sir, it is like basically like a user type of vehicle with that center tab being one sliding jockey kind of thing.
Jockey center tap transformer. Okay, center tap transformer. That's it. The center of the transformation. I'll explain. I'll tell you. Now don't speculate. Don't speculate. Don't speculate. Now here you see. Here if the current is entering this, and if the dot is here, that means the current is also entering here. That is the symbol. That means if this point is positive with respect to this, then this point will also be positive with respect to this. That is the idea. Got it?
Yes.
Supposing it is 1:1 ratio. 1:1 ratio. That means if this voltage is 5 volts, okay, then this voltage will also be plus 5 volts. If this is minus 5 volts, this is also minus 5 volts with respect to the opposite terminal. Got it?
Yes.
So here also. See here also. Supposing the number of windings here is n. Suppose number of windings here is n and the number of windings here is n. N between these two and n turns here and n turns here. That is the here. So here it is. This is n turns and this is n turns. Here it is n. Got it?
Yes, sir.
Now I'll make the dots here. That means now if this is 5 volts, if this is 5 volts with respect to this, okay, then what is this volt? So this will also be plus 5 volts with respect to this. Got it? Hello? Hello, are you with me?
Yes, sir. Yes.
So this is plus 5 volts with respect to this, and what will be this?
Minus.
Minus 5 volts.
Minus.
When this is plus 5 volts with respect to this point, then this is plus 5 volts with respect to this, and this is plus 5 with respect to this, or this is 0 with respect to this. Understood? So the idea here is, now you see, you try to understand this. Now this is plus 10 volts with respect to this. This is plus 10 volts with respect to this. Correct?
Yes, sir.
Okay, so that means now here, if the waveform is like this, at this point, then with respect to this, the waveform will also be like this. With the waveform of this point with respect to this point will be like this. What will be the waveform of this point with respect to this point? Now this one I will take it as the reference point. What will be the waveform of this with respect to this? The waveform of this with respect, the waveform of this point with respect to this point will be like this. Correct?
Should be same as.
The C should be same. Ignore it. I will keep the negative of the probe. I have something called as oscilloscope. I keep the negative of the probe of the oscilloscope here and see this voltage. So when I see this voltage on the oscilloscope, I will get this waveform. Agreed? Hello?
Okay, that part.
Now I am going to see this with respect to this. See, this is minus, I told no.
Yes, sir.
Then it will be like this. Then it will be like this. Correct?
Yes, sir. Yes, sir.
So if I name this as A, B, C. So this is B, A, B. This is V, C, B. This is V, C, B. It will be like this. Correct?
Yes, sir.
And now if this waveform becomes like this, then this waveform becomes like this waveform becomes like this. Understood?
Yes, sir.
Now you see. Now to this point, if I connect a diode, to this point, and to this point, if I am going to connect a resistor and connect it to the diode, then during this positive excursion, this point is positive, but this is negative. So I will be connecting here one more diode, like this, to this common. Okay? Now you see. As far as, so there is diode number 1, diode number 2. So diode number 1 is forward biased. So this diode is on, the current will flow like this. Okay, but this diode is off because this is negative. This diode is off. So no current will flow through this. So whatever current will flow through this, the current will flow through this and go through this. Got it?
Yes, sir.
No current will flow through this during this excursion. Now, during this excursion, okay, this is now negative. So this diode is off. Okay, but this is positive. So this diode is on. So now what happens? The current now will flow like this. This is on. The current will flow through the load like this. Correct? So during this cycle, this diode will conduct. During this cycle, this diode will conduct. But the current in this load will always be in this direction. Correct?
Yes, sir.
So the voltage across this resistor will be again like this. So this is another type of full wave rectifier. So in this case, we are using what is called as center tapped transformer. Center tapped transformer. Correct?
Yes, sir.
Now you see. Now, when this diode, see, in the first cycle, this diode was conducting, this was not conducting. So this was not conducting means, what is the voltage across this diode? Peak inverse voltage across this diode.
Be same as that of the improved.
Which are not here. See, this diode is conducting, So this point is plus 5 volts with respect to this. So this point is plus 10 volts with respect to this. So this diode is conducting, so this is short circuit, and this point is connected to this point. So this point is plus 10 volts with respect to this. So the peak inverse voltage of this is 10 volts.
Sir.
Like that only, this peak inverse voltage. In the formal, this one, the peak inverse voltage was equal to the transformer voltage, half wave rectifier. In full wave rectifier, this is it. But in bridge configuration, you remember in bridge configuration, previous, in the bridge here, the peak inverse voltage here, V0 minus V0 is shared between two diodes. The peak inverse voltage is shared between two diodes. So here, but in this case, okay. So in this case, the peak inverse voltage of each of the diode has to be double the transformer voltage. Okay, so these are the calculations that you have to do. Anyway, we'll take some numerical, there you will understand it.
Yes, sir.
Okay, so you will find what are the differences between these two, this one, and all those things. So you will have to negotiate all this. But if you know the theory, then you can negotiate all of them very, very easily. Okay, so